Hello, we're Team 1 and our topic for today is data augmentation for CNN model. So for this purpose, the data set we've used is Sifferton data set. Before jumping into the implementation of data augmentation in a model, let's actually see what is data augmentation and why do we actually need it. So what is data augmentation? So these days we have a lot of data and a lot of different problems coming up with images, videos, and everything. So talking about problems, computer vision problems which deal with images. So training an image is not really easy. We have to extract information from the image and try classifying accordingly. So for this task, we generally require a large amount of data. So when we actually require large amount of data collection tends to be expensive. So for this task, we can actually use data augmentation, wherein you just take the images that are already in the training set and then manipulate them to create altered versions of the same image. So this way you get, like, say from an image you get like 220. This is just an example. So this is how it goes. You just keep altering, and there are n varieties of altering an image so that you can just populate them and you can use them for training. What do you think could be the advantages of data augmentation? So one could be, as we already spoke about, high expense. So you can overcome the high expense of collecting training images. One more could be it would make your model more robust, because here you're applying like a variety of alterations to your data, like your coloring, lighting. It makes your model more robust. Next, let's actually see what happens to a CNN model when data augmentation is applied. The diagram here you can see is like how a usual training goes. Like you have these images, say this is one image shown here, you just load the image in the label and then a CNN model is trained and then you just compute the loss. So you get the model performance. Here a transformation is applied and then you train. So see here there's two here. So this is how it actually goes about. You can just try n number of alterations and train a model and compute the loss. Now there are so many types of data augmentation that could be applied to a particular model. So these are some of them, like feature standardization, random shifts, scaling. So what we did was we tried applying each of them to our data set, and then we exactly wanted to see how each and every type of data augmentation works with the given data that we have. So here are some of the samples that we had got. So after trying each type of the data augmentation, we tried to pick up random 9 images and just plotting them to see how it works. Here you can see feature standardization. What is a standardization? It's nothing but just throughout the data you have a mean of 0 and standard deviation of 1. That is your feature standardization. These are the 9 random images that we picked in. And what is ZCA whitening? It's like take an image and you just get the important parts of the image highlighted. Like you can see this, you can only get this important part is highlighted here. So this is a random rotation, so you can give any degree for rotating it. Shifts, again, they can be horizontal, vertical. Again, you have flips, those can be horizontal, vertical. So they're just sample of what we had plotted from our given data set. Now, comparing our model performance before and after augmentation, or say how a model actually took this process of data augmentation. Now we had observed some of the things, and let's discuss about what we had exactly observed. So applying a data augmentation to a model, to this given CNN model, we found that there was increase in the model accuracy. So the model tended to perform better after applying data augmentation. We pointed out some differences that we could actually find after processing data augmentation. So one could be the model performance, as we spoke about, and the one more important thing is the model training time. Now, all of us know that the task is huge since we're all dealing with images here. So we also wanted to compare how important the hardware is in this case, like using a CPU and a GPU. Now using CPU, it takes really long time to train, be it a model with data augmentation or without. It does take really a lot of time. So now comparing the time taken for a model with data augmentation, without data augmentation, With data augmentation, it was taking like 20 minutes to run a single epoch. That's like 200 minutes for just 10 epochs. But whereas while comparing for a model without the data augmentation, it was just taking 3.5 minutes to train. But yeah, you could find a lot of difference, like you have model improvement, performances improved and everything. So now let's see the inference of what we actually learned about data augmentation or what we could find. So one important thing as we spoke about is the model training time is increased when we apply this data augmentation. So it's like almost more than twice. Now time constraint, what do you get from this? So time constraint is very important while choosing a model type. So whenever you want to choose a model, make sure that you have good computational power in your machine. So it's like the gap between the computational power and the accuracy. So you before you actually decide on whether to apply this to your model or not, you also got to check like how much accuracy has increased or the problem of overfitting or underfitting or anything any other concerns they have actually it's not there when you apply data augmentation or you have good benefits from it, only then you just got to apply it because it does take a lot of time and that's really a important concern. And one more thing is that it not only benefits the classification task that we're trying to do here but also improves the state of algorithm. The algorithm tends to get better. And imagine we have a situation where the data that we've got is unbalanced, so using this we can actually balance our data. So say we have a classification task and it is a binary classification. So imagine one type is like we have 80% of data belonging to that type and the other type is just 20%. So what we can do is we can apply image augmentation and we can try to bridge this gap between them and make the data balanced. So this is really a great thing. Next is since we've always been talking about timing and how long it takes, there's one thing we can do. We can actually transform images that can be saved to file so that we can use them later. So this can be like one way of saving time. So these are the inferences we have got.